Hello everyone. In this segment we will discuss about another two important properties from discrete Fourier transform. Initially we will discuss about convolution in time domain property, and later on we will switch to multiplication of two sequences in time domain property. So let us start with the first property and somewhat important in terms of analysis of any signal, which is called as convolution in time domain property. So the statement is, if we have two sequences x1 of n and x2 of n whose respective DFTs are x1 of k and x2 of k, then the convolution, now here it will be a circular convolution of these two sequences in time domain, if you take its Fourier transform, it will be multiplication in frequency domain. That means simply we can state this as convolution in time domain is nothing but multiplication in frequency domain. Now the concept of convolution will remain same for entire transform techniques, only the notations are going to be changed. Now let us come and see how to prove this particular property. So for that case, simply we'll write it here as usual, proof. Now we have to find Fourier transform of this sequence, so you can write DFT of x1 of n convolved with x2 of n is, which we can write is equal to summation 0 to n minus 1 x1 of n convolved with x2 of n, and this is multiplied with the exponential term e raised to minus j 2 pi kn by n. This will be our first step, that is writing the formula for DFT. Now in order to simplify this particular term, we will apply the formula for convolution. As you know, convolution of any two sequences can be written using the formula for LTI system, that is linear time invariant system, which I am simply writing here n0 to n minus 1 as it is, and this simplification I am writing in terms of another variable as small m starting from 0 to n minus 1. Now the first sequence will remain as it is x1 of m, and second sequence will be shifted by m unit, so that will be x2 n minus m. Now how it actually comes, or what will be the formula that we are using, you can go and check out in the videos that already being described in signal and systems. Into exponential term will keep as it is j2 pi kn divided by n. Now we'll make certain changes, that means just reallocating the terms. Here we'll write all the terms with variable m, that is x1 of m, and in this case we will put it for n variable as x2 n minus m into our exponential term e raised to minus j 2 pi kn by n. Here it is. Now in order to simplify further, if you concentrate here, we have a term called as n minus m, so we can go for as usual substitution method. So we will put it here, let n minus m is equal to p. That means we are assuming this as another variable p. If I make that change over here, here it is n, so I can write n in terms of p and m as p plus m, and again if you see the limits are going to be changed when we put n as 0 here. So m becomes equals to minus p, and when we put upper limit as n minus 1, in this case this becomes n minus 1 minus m is equal to p. That means we can write simply p is equal to n minus 1 minus m. That means we got both the limits, lower limit as minus m, upper limit as n minus 1 minus m. If it is there, we will make these changes in the given equation or set of equation which we have. We'll put the first term as it is m0 to n minus 1 x1 of m into this limit. Now it will be changed, p is equal to minus m you can see it here, this minus m, and upper limit n minus 1 minus m into x2 of, instead of n minus m we'll put as p into e raised to minus j 2 pi k, and instead of n we can put this as p plus m. So this is p plus m divided by n. Now we have to make or simplify this term. Here the variable is m and here the variable is p, so I can simplify this exponential term along with p and m, so that we'll get this term as m0 to n minus 1 x1m into e raised to minus j 2 pi km divided by n. And in this case, if you observe, when I put m as 0, so this becomes n minus 1 minus 0, that means it is going to be n minus 1. So when we rearrange this term, it becomes p0 to n minus 1. Here the lateral adjustment is quite important. This term as it is x2 of p into e raised to minus j 2 pi kp divided by n. Now this is the formula for x1 of k and this is for x2 of k, and these two are in multiplication with each other. So finally we will get this term x1 of k multiplied with x2 of k. That will be our proof. So in this way we have proved that convolution in time domain is nothing but multiplication in frequency term. I hope you understood this property. Now let us come across the second property, which is multiplication of two sequences in time domain. So as usual, we are multiplying these two sequences, and when I find its DFT, it will be equal to convolution in frequency domain. So in any way we can say that it is going to be a reversal of convolution property. Now let us see how to prove this property. So for that case, first we will try to find DFT of these two multiplication sequences, which I am writing as DFT of x1n into x2n is, which is equals to, again the summation term will remain same, this is x1 into x2, and these two multiplication terms are multiplied with exponential. This will be our formula. Now when we want to proceed further, just observe the RHS term. Here we need 1 by n, and 1 by n can be obtained by using IDFT. That means either we have to find, or we have to write x1 of n or x2 of n in terms of IDFT, so that we can get the term as 1 by n. So here we will make the changes, and I am simply writing the first term as it is, that is x1 of n, and instead of x2 of n we will write the IDFT term, which becomes 1 by n, and here we will assume as variable L. Here I am not assuming the term as k. The reason is already we got the term as k over here. So if I use k, possibility is what, these exponential terms may get cancelled. That's why we are considering this variable as L. This term becomes x2 of L into e raised to plus j2 pi ln divided by n into e raised to minus j2 pi kn by n. See it here, if I use this term as k, this will be k, base will be same, and this may get cancelled, hence I use this term as L. Now let us rearrange the terms. I will take 1 by L outside, so 1 by n we have taken outside. This is L0 to n minus 1, respective term is x2 of L. Now remaining terms will arrange. This is n0 to n minus 1 x1 of n. Now here when we observe this term, we can take power commons because the base is same. So if you take e raised to minus j 2 pi as common, this term will be written as k minus L n divided by capital N. You can see it here, this becomes minus k, already the term is here, and this is minus plus L, this term is already being available. Now when we observe this entire equation, this is nothing but Fourier transform of k minus L. That's why I can simply write this term now as 1 upon n L0 to n minus 1. This is x2 of L, and this will be Fourier transform of k minus L. Now if you see this particular term, it is as good as convolution. That's why we can write 1 upon n as it is, and this becomes the formula for convolution. That is nothing but x1 of k convolved with x2 of k. Now how it comes, already we have seen in terms of, or in case of convolution property, where we use the first step in terms of m and n, that will be the result. I hope you again understood this particular property also. Thank you very much.